Okay, I think we'll get started. So today we're going to start at the final project here. Just I think it's make it a little easier to understand if you see what's going on here. So we're going to create this project where we have two input pins active, GP1 and GP2, and one output pin. And with the two inputs, we're going to get four different states that can come out of the outputs. We're going to control those states with these dip switches here. So let me start here. This would be in the off or 0 position. And we're going to get a blink rate of about 10 hertz or so. Then we saw this is where we were, where GP1 is 1 and GP2 is 0. And we see a different frequency. Let's now, here's intermediate frequency with GP1 being 0 and GP2 being on. And then finally, let's bring them both on. And we see a much slower frequency. So with that, we're going to now talk a bit, we'll go to the whiteboard, talk a bit about what we're going to do, and then we'll come back and look at the assembly code for that. So this is the 4-state blink control lab, and now we will be using two input pins, GP1 and GP2, to control GP0 with 4 possible different states. And here we're utilizing input-output, utilizing the memory, and we are doing some recursive calls. Now, how does this work? Well, this is an important logic table here where we have two inputs giving rise to 4 different outputs, and those are the combinations of 1s and 0s that can be present at these two inputs. So 0, 0, we'll just for the sake of example, we'll set that to about 10 hertz. 0, 1, we'll set that to about 3.5 hertz. 0, 1, 0, we'll set that to 1 hertz, and 1, 1, we'll set that to 0.5 hertz. And we'll do that by just controlling the value we give to the delay. And so we've had the lab on the blinker and seeing how the delay works, and changing that value gives us different blink rates, and that's what we're going to do here. So each one of these different inputs is going to correspond to writing a different value that we will to memory that will then call to set the frequency for the output. So what's going to happen here is we're going to first check GP1, and based on whether that's a 1 or a 0, that's going to call a different function that will then check GP2 and check GP2, and then that will in turn call another function that will then write the appropriate delay value to give us the frequency we want. Now, as you know, the PIC10F200 has a limit of a double recursion, or 2 you can call and then call within a function, and then after that it doesn't work, or you might get nonsense. So we're at the limit here. We're going to call a function inside another function, but we can do that with the PIC10F200. It's got that capability. All right, let's go back to the code now and see how this all works. All right, I'm going to check this cam, make sure, yeah, good, it focused. All right, so let's look at the code here. Again, we start with this boilerplate, and so this is all just making sure that the watchdog's off and the master clear reset is off, bringing in the header file, for PIC10F200 so that it knows some of the addresses and opcodes and such. Then setting the program counter to start at main. And now we go to main, and again we have this boilerplate that we've made up here of setting inputs and outputs. So this first binary literal is going to be setting the output of GP0. That's what we want, GP0 to be an output, and then GP2 and GP1 as inputs. And so those are going to be the two inputs that we receive. Now we are going to write that to the tris with this tris command. And then finally, we don't need to do this, but we'll always just, oh yeah, actually we do need to do this. We need to set GP2 as a input output rather than an external clock. And so that's what we do with this binary literal and then writing to the options here. Okay, so we enter our main loop, and what we're going to do here then is we're going to first test GP1. And so this is bit test this skip if set. So it's going to look at GP1. If it's set, if it has a 5 volts, it's going to skip the next command. But if it's 0, it's going to go to the next command. So let's say it's 0. Then we will go to the GP1 clear function. So this says GP1 is clear or 0. So that's what we name that function. So let's go down and look at that one. So it drops us over to here. Now we are going to check GP2. So GP1 is already clear. We're going to check GP2. And if that is set, it will skip the next one. And then it will check here. So this is often something that we need to do to check the two states, is we put check if it's clear, then check if it's, or check if it's set, then check if it's clear. So let's say it is set. Let's say GP2 is set. So that means it skips this and it goes to here. Well, if GP2 is set, then it's not clear, and so it won't skip that. So it's got to hit one of these two, and only one of these two. And so then we will call GPB. So this is going to represent the 0, 1 state. Had this been clear, then we wouldn't have skipped it, and we would have called the 0, 0 state. So we now we're going to have 4 other functions that are going to be called within these either GP1 clear or GP1 set functions. And those are called A, B, C, and D, as was on the chart on the whiteboard. So let's say we ended up here in this case. And so this kicks us to, actually, let's see. Let me check I'm gonna just put the setting to that so we can see what's going on there. So now we're going to call B. So B is down here. And all this does is it moves the literal 35. And so this is the frequency coming from the way we've set up our delays in this series. So essentially 35 cubed, and then we divide, we take that and divide that into 153. Again, this is just the empirical value that I've kind of estimated for getting the correct frequencies. And so this gives us roughly a 3.6 hertz blink, as we can see on the screen. Or it will give us that. So this is saved to one of the registers, 17, and then this is returned. So we return, and I may not have said this as much in some of the previous videos, but when we call a function and then we return, we need to set this to the working register to 0, and then again we need to have this no op here because sometimes it gets a little funny with the return. So just add a no op. It's not going to do anything. I'm not quite sure why these need to be here, but I've discovered that they do, and I don't really understand it. Okay, so this brings us back. So now we get kicked back to where we were. So I think we were right here. And then now we're back in the GP1 clear function. Okay, we're done now. And so then we return literal, put this no op, and that kicks us back up to here. So we've come up to here. Now it'll check GP1 to see if it's clear, skip if it's clear, and it was clear because that's what the example we were using. So that will skip, just go to no op, and then that'll drop us into the blink routine. And once we have the blink routine, then it will call the memory from memory. So it'll set GP0, so it'll set it high. Then it will move the value that we just stored from function, in this case B, into 17, and then it'll delay, then it'll clear, so turn the LED off, set for that same, we're making a symmetric blink here, and that same value, and then it'll go back to the main loop. And although not strictly necessary, this is nice because it will allow us to break out of this loop, the blink loop. See, we could just go back to blink, but then you're stuck and you'd have to restart. Now we can, if we go to main loop, then we're always testing this again. And it's on this time scale, it's so fast, we don't even notice it. So we're testing this, and it'll catch if we change the values. It'll catch those and then give us the different values. All right, let's just go back and explore these functions again. So notice we had set these into 17, and these different values then we've just decided arbitrarily as our example to use, and so we could change that to whatever we want. And we now have all of these different values. Let's say you wanted to do some pulse width modulation and you wanted some different, you didn't want it to be symmetric. Well, you could easily just write two different values to two different registers, and then back up here, when you call the on and off, say use register 17 and register 16 for the off. So there's lots of versatility that you could have with this. This is pretty much a straightforward function. And so that's basically it. We can see now we have a lot more dynamic control by adding these inputs, and we multiply basically our inputs and get by using the combination of the two inputs, we get 4 different outputs. All right, before we close here, I think that covers the program pretty well. Before we close, let's just take a look at the circuit. Circuit, very simple. These wires up here are simply to connect with the PIC10F200 so that it can program the PIC10F200. These two yellows are connecting to 5 volts and to ground. The output is connected to the LED circuit. This is just a current limiting resistor here, so we don't fry the LED or drive the chip too hard. The inputs then, this is a dip switch, and these are connected with a 10K resistor to ground. And so when they're in the off position, the voltage on the input pins here is 0, and when they're on the on position, these are connected to the 5-volt rail, and so then that gives 5 volts to the input pins. So that's how we test on or off. Okay, so we've got this all ready. Now we want to actually program this, and let me show you something that took me a while to figure out, and this is something that can really throw you. Sometimes the PIC kit interferes with itself when trying to write the program, because you have to have the wires connected from the PIC kit to the PIC10F200, but you also have that in circuit, and so it really is quite remarkable that you can do this programming in circuit, but sometimes it hangs up. So let me leave the configuration the way it is now and try to run this program, and we're going to get an error. So I'm going to go ahead and build it, and we get a successful build, so we know our code is okay. Now let's try to write this to the chip, and program did not complete. Now the reason it's still blinking is because the program just failed, and it's just running the program that was already on the chip. Had we put in a fresh, brand new PIC10F200, we wouldn't get any output here. Now, notice I'm going to change just the 1 pin. Is that what I want? Yeah. So this is on GP1, and I'm going to change that to 1. And let's run this again and see if we can get it to be successful. And it is. So programming complete. So notice what happened if this there's a pin that goes to the same pin as GP1, and if that's in the plus 5 volt position, it somehow interferes with the programming and blocks the programming. So again, when this is down, now GP2 doesn't matter. I can put that in either. So that worked when it was up. It's going to work again here when it's down. But now if I turn this up, program did not complete. So we see here that that's the culprit. And so just make sure that, if it's just, you got the program right, but it's just not writing to the chip, make sure you see what's on all of the inputs. This does happen also sometimes with the GP3 as well. And so I'll try to catch those as we go through different programs. But it's easy to miss that and then kind of chase your tail for quite a while. So let's just finish this off, make sure that it is working here, and programming complete, so everything is working. I should say, if you wanted to make multiple copies, you can just plunk in another PIC10F200, hit the right to the chip, and it's very easy to make a whole bunch of copies of the chip if you need to do that ever. All right, so I think that is everything that I wanted to say for this multi-blinker. And so go ahead and try to make some changes to this and see if you can get this to work a little differently. Note, I guess before we finish, note that to take this same strategy and try to go to a 3-input, we would run into the recursion problem. So we would need a different strategy. This only works because we can go a twice nested call function. So we'd have to have some other clever idea to figure that out. So we're stuck here with the 2 inputs and the 4 outputs. But play around with that, see if you can get this to behave a little differently.